All right, so let's continue. So for spring 2026, we know that we are going to skip this part. So no RCLB. And then also we said no efficiency only for fall 20, I should say spring 2026. All right, so let's go ahead and proceed. I want to find exact distribution of the MLE. Remember that we identified the MLE as X bar. Okay, so for part C, we know that the MGF of X bar be that, which is going to be essentially the MGF of the summation of the XI's evaluated at T over N, which is going to be the product of the MGF of the XI's evaluated at T over N. We know that XI is exponential. And so therefore, it's going to be 1 minus theta T over N to the negative 1. Okay, so that gives us 1 minus theta T over N to the negative N. In other words, X bar is gamma N and theta over N. Alrighty. Okay. Part C is what we just did. Part D says describe how you would construct an exact 95% compensate interval for theta. Okay, so part D, describe means essentially do it. And we can use the gamma distribution itself, but since we're so close to a chi-square, I want to just make this a chi-squared. To make this a chi-squared, we need this item, beta, to be 2, right? So if we multiply things accordingly, I think we can make it happen, right? Now, how can we identify what we need to multiply by? Well, notice how this 1 over n, right, which is the coefficient of t, is what shows up here, 1 over n, as a coefficient of sigma. So if we want, did I say sigma? The coefficient of theta, I need to sleep. All right, so what needs to happen is instead of just the 1 over n, what if we had the no 1 over n and we just had a 2 over theta? If I had 2 over theta, the over theta would cancel this theta, and then the 2 would be would remain, right? If I didn't have the over n, then I wouldn't have the over n problem. So in other words, we need to multiply what we had before, which was X bar, by 2 over theta. Okay. So consider W equals 2x bar over theta, right? Then M sub W of t is expected value of E to the 2t over theta x bar. Matter of fact, 2t over n summation of the x's, right? We could write it that way instead of the x bar, which is the MGF of the summation of the x's evaluated at 2t over theta n. Okay. And I'm seeing that the n came from the x bar, right? So I think I said we should multiply by n, but I didn't do it. So I'm just going to get rid of that n by multiplying it by another n here, okay? So we need an n here, 2n x bar, which would be 2 summation of the xi's over theta. Alrighty. So that right there, we'll get rid of that n in our denominator. And That will give us product I equals 1 to n. The exponential MGF 1 minus theta t, where your t is 2t over theta to the negative 1. That's 1 minus 2t to the negative n. And so our quantity, W, is chi-squared with 2n degrees of freedom. Okay. So then, if that's the case, we can use a pivot method, right? It's based on the MLE. So let me be more specific and say W is a function of theta hat MLE. Check. Number 2, our expression is a pivot. How do I know it's a pivot? It's a pivot because it has a chi-squared distribution, and chi-squared has no thetas in it. And also it's a pivot because it's a function of theta. Number 3, make a probability statement. Chi-squared, what's the percentage? Okay, 95%. Chi-squared 0.025 is less than W. Less than chi-squared 0.975. Okay, where again the picture you want to think about right there is chi-squared 0.025 right there. Chi-squared 0.975 right there. 0.025, 0.025. And then we can solve for theta in the middle. We'll reciprocate and multiply. So we'll have 2 summation of the xi's over chi-squared 0.975 less than theta less than 2 summation of xi's over chi-squared 0.025. This right here will be our lower limit. For the confidence interval, this will be our upper. Alrighty, and then yeah, that's step 4. So that's our confidence interval. Part E, what's the asymptotic distribution of the MLE? So for part E, since the MLE is a mean, we can use a CLT. Radical n x bar minus E of x converges in distribution to normal 0 variance of x, right? That's a CLT. Plug and play. This is going to be radical n x bar minus theta because expected value of the exponential is just theta. The variance of the exponential is theta squared. That's part E. Part F is an approximate confidence interval based on the CLT. So for part F, what we're saying is, well, x bar minus theta over theta over radical n should be converging to a standard normal as an extension of the central limit theorem. Okay. And so this is our pivot. And so we use a pivot method on this quantity right here. Okay. We can say the probability z, let's say negative z 0.025 less than x bar minus theta over radical n less than z 0.025 rather. Do it like that, where the z quantiles are exactly what you expect them to be. Negative z 0.025, z 0.025. I know my notation with the subscripts is not consistent, but hey, at least it converges in distribution. All right, so we can solve for theta in the middle. And so typically how this is done is the following. We can say this is x bar plus or minus z.025 times theta over radical n, okay, is a 95% CI for theta. You say, hey, that CI incorporates theta. You're right. So we'll just go ahead and put a MLE. We'll use the MLE to estimate the standard deviation, but we won't use it to estimate the unknown parameter, so to speak, explicitly, or to plug in for that parameter. This is a common issue in stats, and it is one way to approach it. Another way you could approach this problem is you could alternatively say in this expression, so this is method one, which if you can do it, just do it because it's satisfactory and it'll save you a lot of time. Method two is where you say x bar minus theta over radical n. You can kind of express that with some algebra. Okay, and say this is equal to x bar over theta minus 1 over radical n. And then that way you can solve for, there's one theta to solve for, right? As opposed to this situation on the left where you have two thetas to solve for. Then you got to do this plug-in principle. So that's just a different approach. We saw it on the chapter 4 or 5 homework. But again, just go this route and plug in. It's just a lot easier to work with.